Hello, everyone. Welcome to my channel. Uh, this is an educational channel. We focus on um, primarily the obscure and esoteric and things that you probably wouldn't know anything about if it wasn't for this channel. And today is video number 208 on the reciprocal system of theory. And this was a theory that was discovered by Dewey B. Larson back in the 20th century. He died back in 1990, but not before. He wrote many books and articles and gave talks on his reciprocal system. The basic idea of the reciprocal system is that we live in a universe of motion. This is a universe that is made out of motion, and motion is the relationship between space and time. So space and time are not the container of the universe, but they are the contents of the universe. And space and time basically really don't exist except together in motion. Motion is basically a fraction with space or time as the numerator and time or space as the denominator. But they do come in multiple dimensions, what Larson calls coordinate space and coordinate time. So there can be multi-dimensions in that fraction. For example, matter is time to the third power over space to the third power, whereas energy is just time over space. And every scientific mechanical or dynamic quality or units is expressible exclusively in terms of space and time. Now, also in addition to their coordinate aspects, space and time also have their clock aspects. Clock time we're familiar with. That is the progression of time. Time is always getting later and later and later and later. And this is in no particular direction. Larson calls that a scalar motion, a motion that has a magnitude but has no particular direction. But there is also clock space. And that basically means that space is getting farther and farther and farther apart. And you could envision this by taking a balloon and putting a bunch of dots on it with a magic marker. You blow up the balloon and all the dots are moving away from each other. That is the progression of space. And then space and time also both come in discrete units, meaning that they are not continuous. They come only in chunks, and they're very small chunks. But one chunk of space in one chunk of time is the speed of light. And so the speed of light, just like all speeds, are space over time. So here you can see, like if you use Einstein's equation E equals mc squared, as we said before, energy is time over space. Matter is time to the third power over space to the third power. And then c squared, the speed of light, is the speed of light is s over t, but you take that to the second power, so you get s to the second power over space to the second power. So if you work out that equation, the units work out correctly. So that is a valid, or at least potentially valid, equation. Now, what Einstein got wrong, or one of the things that he got wrong, is that he said that the speed of light is the maximum speed of the universe. But in Larson's system, the speed of light is one unit of space over 1 unit of time. That equals 1. And so in Larson's system, the speed of light is the midpoint of the universe. There is half of the universe that is actually moving faster than the speed of light, which Larson calls the cosmic sector. And there's the half of the universe that is moving slower than the speed of light that Einstein was aware of, and that all legacy scientists are aware of, where they make their measurements and their observations, and that's called the material sector by Larson. And we basically understand what's going on in the material sector, but we know nothing about the cosmic sector. But since uh, there since there is a reciprocal relationship between space and time, all we have to do to understand the cosmic sector is reverse the roles of space and time. So what we know about the material sector can basically be transferred over to the cosmic sector as well. For example, you have your in the material sector, we have coordinate space, three or more dimensions of space, and then we have clock time. The clock is always getting later and later and later. But in the cosmic sector, we have coordinate time, three or more dimensions of time, and we have clock space. So we reverse the roles of space and time to figure out or to have some idea of what's going on over in the cosmic sector. Now, we are looking at Larson's 1979 book that's called Nothing But Motion. And this book is primarily on atomic physics. Now, in Larson's world, an atom is a combination of motion. He used the analogy of a curveball. A curveball is one thing, but it is a number of different motions. There's the translational motion of the ball that when you throw it, it moves forward. But if you're throwing a curveball, you're also putting a spin on the ball at the same time. So that's really like a combination of two kinds of motions. But those motions are not, but the curveball is just one thing. Okay, now in Larson's world, an atom is really a combination of a few different kinds of motion. First, you have two photons at the core of an atom, and a photon is also a combination of motions. In Larson's system, a photon is a translational motion and also a vibrational motion. That vibrational motion is in a perpendicular dimension to the translational motion. When you put them together, you get a sine wave or a simple harmonic motion. Now, Larson's some of his followers rejected that notion and said that a simple harmonic motion, a wave-like motion, is actually the combination of a birotation. Two rotational motions combined together turn out to be, when they interfere with one another, that also can create a simple harmonic motion. So there is a dispute there as to what is at the core of the atom in terms of the photon. But then once you have the photon, then you can rotate the photon in other dimensions that are also perpendicular to that photon. And when you rotate it once, you end up with a disk, and then when you rotate it twice, you end up with a sphere. And so the atom is a combination of two, what he calls two-dimensional rotations, a primary and a secondary two-dimensional rotation. And then there is also an optional one-dimensional rotation in the atom. So in Larson's system, an atom is a three-numbered group, A, B, and C, A-B-C, which entail the first two-dimensional rotation, primary two-dimensional rotation, the secondary two-dimensional rotation, and the optional electric or one-dimensional rotation. Now, in this chapter, we're in chapter 16 that is called Cosmic Atom Building. He's talking about cosmic atoms. And so a cosmic atom is the same as an atom, except that you reverse rules of space and time. So in an atom, you really have the photons being more or less in time and the rotations being in space, or vice versa. Um, and then the cosmic atom is the reverse of those. Now we see cosmic atoms are, the chapter before this was called cosmic ray decay. A cosmic ray is a cosmic atom, but it's what we see, the way we see a cosmic atom. The only way that we're actually, the boundary is the speed of light. When we are able to see a cosmic atom when it comes across into the material sector. And the way that an atom is ejected from the cosmic sector into the material sector is through a powerful explosion of a cosmic star or a cosmic galaxy. Just like from the material sector can break into the break the boundary, the speed of light boundary, by supernova, a powerful stellar explosion, or a galactic explosion, which Larson calls a quasar. And that can blow the atoms of that star or galaxy across the boundary into the cosmic sector. But when atoms go across the boundary, they immediately become unstable, radioactive, because they're not, they don't have their motions in time or space in the right kind of configurations. So the cosmic ray decay is when the atoms, cosmic atoms, come into the material sector. They're immediately unstable and they start to decay. They basically decay up the periodic table. So what we generally see is, we see, to start with, a cosmic helium or cosmic hydrogen, and then as it starts to decay, it moves up the periodic table all the way up to cosmic krypton, where it can reverse, and then it turns into two material massless neutrons. And in the same way, it works in the cosmic sector, but we have to, or in the material sector, but we have to understand that we see space, but we do not see time. And so the only way we see time is how it affects space. So for example, with a supernova, an exploding star, if the star is exploding powerfully enough, then it explodes into the cosmic sector, meaning into coordinate time. And so the star is exploding in time, but we don't see time, we only see space. So what we see is the inverse of explosion in time. We see an implosion in space. And so that creates a highly compact, super dense star that is called a white dwarf. Or if it's a galaxy, it's a highly compact, super dense galaxy, which is a quasar. Another form of a highly compact, super dense star is a pulsar. So, okay, now we've been going on here. We're going to talk about this cosmic atom building sequence. We just went, in the last episode, we just went over the table here. So he's going to be commenting on this table of all the different resonances, that cosmic atom building sequence that we went over in the last video. So you refer to the last video if you want to get up on this. Otherwise, do the best to take over from here. Most of the reported experimental results omit many of the steps in the full sequence. Whether this means that double or triple jumps are being made, or whether the intermediate stages have been missed by the investigators, is not yet clear. However, the most complete set of results, the sigma series, is close enough to the theoretical sequence to suggest that the buildup does, in fact, proceed step by step as indicated in Table 4. Regardless of any deviations from the normal sequence that may take place earlier, The first phase of the atom building process always terminates at C lithium 5, the omega particle mass 1676 mega electron volts, because, as is evident from the description of the steps in the cosmic ray decay, the motion must enter a second dimension in order to accomplish any further decrease in the cosmic atomic number. This requires a relatively large increase in energy from 1676 to 3104 mega electron volts. In the decay process, there is no alternative, and the big drop in energy must take place. But in the reverse process, the addition of energy in smaller amounts is made possible by reason of the ability of the cosmic atom to retain additional gravitational charges in an excess energy environment. The doubly charged cosmic element of lowest energy within the atomic building range is C krypton, the first atom that can be formed from conversion of material particles. The energy difference between doubly charged C krypton and the last singly charged product, C lithium 5, is substantial, 238 mega electron volts. And all of the cosmic atom building series theoretically include doubly charged C krypton as well as singly charged C lithium 5. There are, in fact, some intermediate stages. All but the last small increment of the mass required for the second charge is added in the form of C krypton atoms, 52 mega electron volts each. As in building up the rotational mass, this addition is accomplished in 4 steps. Similar interstages are possible between C beryllium 7 and C lithium 6, also between C lithium 6 and C lithium 5, where 2 cosmic krypton mass increments are required between the cosmic elements. Beyond doubly charged C krypton, the regular sequence is again followed, with some omissions or deviations, which, as mentioned earlier, may or may not represent the true course of events. At doubly charged C lithium 5, mass 2607 megaelectron volts, the atom building process again reaches the one-dimensional limit, and a third range is added in the same manner as the second, inaugurating a new series of resonances which extends to the neighborhood of 3104 megaelectron volts required for the production of the first of the particles that have scalar motion in 2 dimensions. Table 5 compares the theoretical and observed values of the properties of the particles included in the several series of resonances that have been reported. The agreement is probably about as close as can be expected in view of the difficulties involved in making the measurements. In more than a third of the total number of cases, the measured mass is within 10 megavolts of the theoretical value. It is also worth noting that in the only case where enough measurements are available to provide a good average value for an additional cosmic element, 11 measurements on C lithium 5, the agreement between this average and the theoretical mass is exact. All of the singly charged transient particles moving in only one dimension are stable against decay for about 10 to the minus 10 seconds. However, they are extremely vulnerable to fragmentation under conditions such as those that prevail in the accelerators, and only the particles of lowest mass escape fragmentation long enough to decay. The lifetime of the heavier particles is limited by fragmentation to the absolute minimum, which appears to be the unit of time corresponding to 3 scalar dimensions of motion, or about 10 to the minus 24 seconds. In the tabulations of particle data in the current scientific literature, The information with respect to the series of resonances thus far discussed is presented under the heading of baryon resonances. A further classification of meson resonances gives similar information concerning particles that were observed by a variety of other techniques. These are, of course, entities of the same nature, cosmic elements in the decay range, and largely the same elements, but because of the wide variations in the conditions under which they were produced, the meson list includes a number of additional elements. Indeed, it includes all of the elements of the regular atom building sequence, with C neon and C oxygen substituted for C fluorine as previously noted, and one additional isotope, C carbon 11. The masses derived from the experiments are compared with the theoretical masses of the cosmic elements in Table 6. The names currently applied to the observed particles have no significance and have been omitted. Now, he's got Table 5 and 6 here, or well, Table 5 before this, and then Table 6 coming up. These are the different resonances. Now, these charts are kind of a little bit too long to go through as we do these videos, but I will attempt to kind of summarize them in tomorrow's video. Now, just for the record, I understand very little of this. Okay, this is really difficult stuff, and you know, I've gone through this many times and I still don't understand it, but each time I go through it, I pick up just a little, and eventually I think it will click. That's kind of how you have to approach Larson, is just hope that it clicks at some point. So just, you know, go over it over and over. Remember that we're learning atomic physics here. This is not kindergarten. You know, this is difficult stuff. And so, you know, in order to learn difficult stuff, you have to apply yourself and you have to persevere. You're not going to pick this up just by watching a 20-minute video. You need to, you know, go over my videos over and over again, and you need to really listen to all of them in order to pick this up. So it takes a dedicated person to be able to understand this, but the payoff is quite fantastic. You know, if you were able to understand atomic physics, you know, that's something that a lot of people would like to be able to understand, and not in the legacy science way where they're putting a lot of band-aids on their lack of knowledge of certain things. But this is getting right down to the fundamentals and getting right down to him basically coming up with a theoretical universe that actually matches up with the observations that were made by legacy scientists. So the legacy scientists can give you the numbers, they can give you the observations and the measurements, but they don't know why they exist like this. Larson is providing the why. And so that's a great key, but it's not something that comes easy. Okay, well, thank you for tuning in, and hope to see you back next time. Otherwise, have a great day.